Hello and welcome to my series on electric circuits. So what I want to achieve with this series is to actually teach you the very basics, but also some of the fundamental principles behind analyzing and designing electric circuits for different purposes. And in this video, what I'm going to do is I'm going to review some concepts that are quite important to know when we're talking about electric circuits in general. So the first thing we need to talk about is about how current flows in a conductor. So essentially, you can imagine that if we have a wire of a certain length L and some cross-sectional area A, then essentially what's happening here is you have electrons are flowing from one side to the other, okay? And in general, they usually flow from the negative terminal to the positive terminal, so there has to be a potential difference between the two ends of a conductor for electrons to actually move. And this motion of electrons is what we characterize as an electric current. This is by definition electric current. Now, generally, any kind of metal or conductor is going to have a resistance. So resistance is expressed in units of ohms. And essentially, this is kind of like something that is slowing down the flow of electrons through that particular metal or material. And we know that if you have something like a metal where the electrons are relatively free to move, they usually conduct electricity very well due to the same reasons. If you have an insulator, then that's kind of a material where the electrons are kind of bound, so it's very hard for them to flow. And as such, when we use things like rubber or plastic, they're good insulators because they do not allow any current to flow through. So that's essentially the principle. Now, the resistance is related to the material properties via something called the resistivity. So that's expressed by the Greek letter rho, and this is times L divided by A. So essentially the resistivity, which has units of ohms per meter, is going to be related to the material itself. It's kind of like the conductivity. It has its own, it's a single value for every single material that you can think of. And the relationship here is actually quite important because what happens when you increase the length of a conductor? Well, you notice that the resistance is going to increase. Let's say that you keep the cross-sectional area constant. That means that the length, as you increase the length, the resistance is also going to increase. And if you do the opposite, let's say that you actually increase the cross-sectional area, then what's actually going to happen is the resistance is going to be reduced or decrease. And why is that? We need to actually wonder why that is. Well, with the length, it kind of makes sense. You have more material to get through, so obviously there will be more loss of energy of the electrons due to collisions. You can think of this in the following way. You have electrons colliding with the walls of that conductor or wire. So as they collide with it, some of that energy is transferred to the surrounding material in the form of heat. And as such, these electrons will lose some of their kinetic energy, which is going to slow them down over time. So if you make this a lot longer, then that means you increase the rate of collisions, which means that there's actually going to be actually it's not really gonna make much. It's just going to mean that there's gonna be more resistance in it, essentially. And this is what happens when you increase the length of the conductor. On the other hand, if you look at the cross-sectional area and you make it bigger, so let's say we compare two different types of conducting wires. So this one is going to be very thick. So you have something like this. Then it makes sense that this one is going to have less resistance to that flow of electrons. And this is due to the fact that now the electrons have a lower chance of colliding with the walls. So they have more space to move around, which means the collisions are going to be less frequent in average, and as such, they're going to lose less energy over time, which means that the flow is not going to be hindered as much as they would if they were constricted in a very, very thin kind of conductor. And that's essentially why, when you're thinking about the resistance or the conductivity of material, you have to think about the dimensions and the properties and so on. So as a general principle, I'm not going to go in a lot of detail into the physics because, as I said before, this whole video series is going to be based on analyzing and designing electric circuits rather than looking at the physics of electricity and magnetism. So we're going to just focus on the basic principles. But now, having said that, when we actually look at some sort of arrangement where you have something like a battery, so remember the longer end is the positive end, and this one is going to be the negative end. And then suppose you have some resistor here. What's going to happen is the electrons are going to flow from the right hand side, in this case from negative to positive. So that's the electron flow. However, we term the current as in many terms we call it the conventional current, which we denominate by I, as being the opposite direction of the electron flow. So essentially it's like, imagine you have a certain amount of positive charges on this side, and then as the electrons come in from this side, those positive charges have to rush back to the other side to kind of make everything balanced in terms of charge. So that's why in general the conventional current is taken as going from positive to negative. It doesn't actually matter in the end, because the only thing that is going to change is just the sign at the end of the current that we calculate. But in general the principles are pretty much the same. But in general we use this as kind of like the regular natural convention for current, and we denote it by lowercase I in the case of electrical engineering. So what we can actually say is that current, represented by I, is simply the rate of change in the charge with respect to time. So current is in general a time-dependent variable, so it depends on the flow rate of electrons or charges. And in general, charge is represented by coulombs, and then time is in seconds. So the units for electric current are coulombs per second, or simply amperes. This is the more common unit of measurement. Similarly, we can have the voltage, which is just going to be represented in volts. And this is often termed the potential difference, so it is between two ends. It's just how much difference in potential is there. Okay? And then finally, we have Ohm's law, which says, okay, the relation between these three quantities is going to be given by V equals IR, essentially. So it is a linear relationship, and in fact, if you were to plot voltage against current, you should get a straight line for most kind of components, and then the gradient of that line is going to give you the resistance. So resistance is a constant, unless it is a variable resistance, of course, it is going to be the slope of that line. And that's basically the principles that we need to abide by when we're talking about these things. There's another quantity called the conductance, which is represented by capital G, and it is just the reciprocal of the resistance. This has units of ohms to the -1, but more commonly it has units of Siemens, so it is represented by S. This doesn't really have that much advantages over resistance, but it is often preferred in certain calculations when we're dealing with large circuits, so you might see this pop up a few times when we're dealing with electric circuit analysis. And that's basically the gist of it. So in the next few videos, we're actually going to go into different rules for analyzing circuits, and we're going to look at many different methods for doing that with different components.